Hi. So I wanted to make a video with a couple more examples of biased exponents and unbiased exponents and floating point representation so that we can see some of the benefits of why we would bias an exponent upon storing it, let's say on a computer or something along those lines. And in this problem, I'm going to give you a floating point system that has 6 bits in it. And I'll tell you that the first bit is going to be the sign of the number. The second bit is the sign of the exponent. Bits 3 and 4 are the exponent itself. And bits 5 to 6 are the mantissa. Now, the first question you should ask yourself, is this system biased or unbiased? And the reason we know the answer to this is depending on the sign of the exponent. If it is present, as we see here, this is present, then that means it is an unbiased system. This is unbiased. The point of biasing is to get rid of the sign of the exponent. We reallocate that bit towards the exponent itself so we can have a bigger range. We'll see what that looks like in these examples. But if the sign of the exponent is there, that means it must be unbiased. So let's go ahead and write out these 6 bits. The sign of the number we've been giving as a sigma. The exponent sign is P. The exponent itself are E's, and then the mantissa are M's. And we want to know, for part A of this problem, what exponents may be stored in the system. Really meaning that the mantissa and the sign stuff we don't really care about at this moment. We're only looking at the range of exponents that can be stored. So let's go ahead and think about this. If I were to look at the sign of an exponent, let's go to the lower end first. Let's look at negative exponents. A negative exponent is dictated by the number 1, as we talked about in class. The way I remember this is that a 1 kind of looks like a negative sign that's been rotated 90 degrees. And I know that the biggest negative exponent I can have will be based on the biggest exponent in general that I can store, which for this problem would be 1, 1. So the biggest exponent would be negative 1 in negative 1, 1 in binary. And similarly, if I were to say, let's make it positive, the only thing that really changes is that this is a 0 now, saying it's positive, and the biggest exponent on that end is positive 1, 1. If we were to convert these to base 10, this would be negative 3 in base 10 and positive 3. So in this system currently, the unbiased system, we can store exponents from our floating point representation that are between and including negative 3 and positive 3. And just to be really thorough about that, this would be negative 3, negative 2, negative 1, 0, 1, 2, 3. Now, one thing that just kind of help you wrap your head around this is that if I give you, and let me move all this other stuff out of the way for a second so that that can have some room. If I give you 3 spots that can contain either a 0 or a 1, that means that each position can have 2 options. I can have this be a 1 or a 0, this could be a 1 or a 0, and this could be a 1 or a 0. Which means we have 2 options per bit, which implies that we have 2 times 2 times 2 combinations of possible 1s and 0s. We have 8 possible combos And you can figure those out on your own, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., all the way up to, let's say, 1, 1, 1. But over here, we have only 7 possible numbers. Why do you think that is? Why do you believe we have 7 numbers in this list, but we should have 8 numbers? Well, the reason is because if we were to do 1, 0, 0, or 0, 0, 0, remember that first bit's the sign. This is like -0. This is like +0. Meaning that our 7th and 8th possible option, -0 and +0, are exactly the same. So we lost a possible combination because of the fact that we are including the signs of the exponents. This is our motivation. So here we have 7 possible options, when we really should have 8. If we have 3 bits, we have 8 possible combinations, but we only have 7 because -0 and +0 are exactly the same. That's kind of our motivation for biasing in general. We would rather regain that 8th possible exponent, and we'll see what that looks like shortly. But that's kind of the idea. Let's go to part B of this problem, which is asking us, can we store the number 20 in this system? So if you're ever asked to find if a number can fit or how would it be stored in a certain system, we first have to convert the number to binary and then the floating point. So convert 20 to binary and then ultimately floating point. So how do we convert an integer from base 10 to binary? We will do a table like we've been doing in class. And since it's an integer, the one that I'm going to do is our value quotient remainder table, or VQR. And we'll start with 20. And we are going to divide by 2 continuously until we can't anymore and keep track of our remainders. So if we divide 20 by 2, we get 10, which has a remainder of 0. It's an even number. We shouldn't have a remainder when we divide by 2. 10 is an even number. When I divide by 2, I get 5. There's no remainder. And again, what I'm doing is I'm taking these quotients and making them my new value. 5 divided by 2 is 2.5, but for this procedure, think about this as long division. We're not going to worry about decimals. We're going to worry about how many groups of 2 fit perfectly into the number 5 without going over. And in that situation, there's 2 groups of 2 that go in. That brings us to 4, which yields a remainder of 1. And again, if you have an even number, your remainder will be 0. If you have an odd number like 5, your remainder will be 1. How many groups of 2 go perfectly into 2? 1 with no remainder. How many groups of 2 go perfectly into 1? None do, with 1 remainder. And then we're done, because if we do 0, we'll have no groups with no remainder. It'll just continue forever. For these, you're going to read from bottom to top, which tells us that 20 in base 10 is 10100. And if we were unsure if that's correct, and we wanted to check our work, we can convert back. Zoom in over here for a second. This is our groups of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. So we have one group of 2 to the 4 plus one group of 2 squared. That's 16 plus 4, which is 20. So we converted correctly, is the moral of the story. However, I did not finish the problem yet. Oops, I lost some things there. I don't care. It's fine. Let's just get to there. Good enough. For this question, it asks, can it be stored in the system? We have to convert the floating point. So we're going to do 1, 0, 1, 0, 0. And let's remember where the radix point is. That's the decimal point in a binary system, is in its normal position. That's all the way on the right. We want to convert this to a floating point representation, which is essentially scientific notation. So I'm going to move the decimal or the radix point over how many spots? Well, I'm going to go 1, 2, 3, 4 spots. 1.0100 times, and instead of 10 raised to a power like we do in base 10, in base 2 it's 2 raised to a power. And we have that because we move the decimal 4 points over. Now, let's see why this won't work. First off, we said here that our exponent in the system can only go between -3 and 3. The exponent in this problem is 4, which means it cannot be stored. Why? Well, the way we would represent this in floating point is to convert that 4 to binary. And a 4 in binary, and you can do another VQR table if you're not sure, is 1, 0, 0. Because 4 is 2 squared. I mean, if you come over here, we can see that right here, 1, 0, 0, that is just 4. And 4 requires 3 bits for the number. We're not including the sign there. I would need 4 bits for the sign, and we don't have that in the way the system is set up. This system only has 3 bits total for P and E's. We would need 4 bits for the number 4. So the question was, can this be stored in this system? No. We end up with an overflow error because 4 is too big. And you can see we're not even worrying about the mantissa or the sign of the number in this situation. I'm just looking at the exponent to see if it's even possible to store it. That's part B. Part C, if biased, what is the range of biased exponents that can be stored? There's your spoiler for later. I'm going to move this down, really down, so I can get it out of the way. It says, if biased, what is the range of biased exponents that may be stored? So let's look at our 6-point system, again, our 6-bit system. And I said that the first bit was sigma, the second bit was P, E, E, M, M. Again, this is the unbiased system, and we're interested to know what is the range of biased exponents that can be stored. So if we remember our range of exponents, it was -3 to +3. 7 possible options. When we bias it, we're still going to have 6 bits. We're not adding more space. We're just changing how the space is being used. We change the P bit to an E bit. This bit is no longer a P when we do that. We're getting rid of the sign. And how do we do that? We have to make sure that our list of numbers that come in, we have to be sure that the list of numbers that come in, they can never be negative. Because again, I might be storing 100 different numbers in a biased system. If the exponent is -3, -1, if it's +2, it doesn't matter. I have to add something to all of these numbers. So all these numbers, we have to add something to bias. What are we going to add? We're going to add 3 because the most negative exponent that is possible that we have to be prepared for is -3. And if we want to get rid of the sign, we have to add 3 to each of the exponents. Which means that if we add 3, our bias is going to be to add 3. We will have a range 0, 1, 2, 3, 4, 5, 6. And based on that, it looks like I have the same number of possible combinations. I had 7 combinations in the unbiased system, and I currently have 7 combinations for the unbiased system. Why would we do this? Well, let's look at the range of ease by looking at the bit stream itself. Let's say I look at the smallest possible exponent that I can store. That is 0. Okay, that's that. What is the largest possible exponent I can store? 1, 1, 1. 1, 1, 1, if we convert that to base 10, is actually 7. Which means that we now have 8 possible numbers that we can store, as opposed to 7. And in the previous system, like I mentioned before, we really had this plus or minus 0 problem. So it was still storing 8 numbers, kind of, 100 or 000, or 2 different bit streams, but they produce the same number. They're both 0 because positive and negative 0 are the same. So instead of having that issue, by biasing, we now have 8 distinct numbers, which allows us to improve what we can store. So the question was how many, or what's the range of biased exponents? The range of biased exponents is going to be 0 to 7. This is 8 possible combinations or exponents, as opposed to 7 before. That's the benefit of biasing. Part D, how would the number 20, how would the number be 20 stored in this system? So let's go see how that changes things. Now, because before we said that 20 in base 10 is 10100, and we said that this was 1.0100 times 2 to the 4th, which is 1.0100 times 2 to the 100. This is the unbiased representation of this number, and we couldn't store that. So what we just said was if we want to bias something, we have to add 3 to the number. So let's add 3 to the exponent. Because again, that's what I set up here. We have to bias by adding 3 to ensure that that is going to be positive in that situation. So we add 3, which would mean that our number is going to be 1.0100 times 2 to the 7th in base 10, which is 1.0100 times 2 to the 111 in binary. And like we just said, I can store up to 7 in the bias system, which means that the number 20 can now be stored in the system. It could not be stored when it was unbiased because we didn't have the right number of bits. But now that we've reallocated the sign of the exponent to the exponent itself, we can store that extra number. So in the bias system, this is sigma E. This is a positive number, so the sigma is 0. The exponent is 111. The mantissa are the bits to the right of the decimal, and if we can't fit them all, we just end up with some round off error. But in this situation, the only meaningful bits are the first two. The others are all 0. So this is the exact representation of 20 in the bias system. I really hope that makes sense. It's a tricky concept, but what we're doing is we're taking a number that cannot be stored as is. We are disguising it in a way with this bias system so that it can be stored. And then if we want to see it later, we'll take it out of the system and then unbias it. And we can see the original number. I have one more example. A bias system with 4 bits. I give you before. It's biased currently. The first bit's the sign of the number. The second and third bit are the exponent, and the fourth bit's the mantissa. And I ask you what base 10 number is stored as 1101 in the system. So our bias system is the sign of the number, 2 exponents, and the mantissa. And when we want to look at what base 10 number is being stored, we don't calculate this number. We don't do, this is -1 point. The mantissa is 1 times 2 to the 1, 0, and then calculate this and say, we got it. We don't do that because that's not our original number. Like in the previous problem, if I recalculated this as is, where the exponent was 7, I definitely wouldn't get 20. It'd be a lot bigger. We have to unbias the bias form to get back the original number. So how do we do that? Well, what we want to do is look at the unbiased case and kind of deduce how do we get to the bias system prior. Because the unbiased system still has 4 bits, sigma, except one of the exponent bits is now the sign bit. Because we got rid of the sign bit when we biased. So now we're trying to figure out how much did we add to the exponent to bias it. So let's look at our range of exponents here. And again, I don't really care about the sigma or the m in this situation. I'm just looking at the p and the e. The lowest exponent I can have would be -1 in binary. And the highest exponent I can have is +1 in binary, which is exactly the same as -1 in base 10 and +1 in base 10. So our range of exponents would be -1, 0, 1. How much do I need to add to bias it? Well, I'm going to make sure that of those 3 exponents, none of them will appear as being negative. So I have to add 1 because of this problem. I look at the worst possible case of a negative exponent and ensure that that specific case is never negative. Coming back up to this one, we looked here at the worst case scenario, which was -3. We added 3 to bias it. In this problem, -1 was the worst case. So if we add 1 to everything, we see that we end up with a system with no negative numbers. And again, when we look at this bias system, I'll just for teaching purposes, not this example, I know that the lowest number I can have is 0. The next number I can have is 0, 1. The next number I can have is 1, 0, which is the 2. But because we're not dealing with plus or minus 0 anymore, we can reuse that spot and get a 3 out. Again, this is the benefit. And the unbiased system, there were 3 possible numbers we can transmit. In the bias system, it is 4. So we have added 1. which means that this number, the exponent already has +1 in it. So to unbias the number and get back the original base 10 value, we'll have to figure out what this exponent is, subtract 1 from it, because we already added 1. We're trying to unbias now. We're going to do the opposite. We'll subtract 1 and then find the number. So this number was 1101 sigma. These were the E bits, and this was the M bit. So the exponent at the moment, and this is the biased exponent because this is the biased system. Really clear, E. This is the biased exponent. This is 1, 0. If we convert that to base 10, this is 2 in base 10. The biased exponent is the unbiased plus the bias, which in this case was 1. Which means that our unbiased exponent is actually 1. So this is the unbiased. And it's +1. If I wanted to look at that in an unbiased system, a floating point system, the M and the sigma are exactly the same. It's the P and the E that are a little bit different. The P is now a 0 because it's positive, and the E bit is just the 1. If this problem was like the first example and I said to bias it, you would end up getting that one because you have to add 1 to the exponent. And then in that case, you would get 2. So how do we convert this back? The sigma tells us that it's negative. We'll get 1 point, the mantissa, which is 1 times 2 to the positive is the P. 1 is the exponent. We can move the radix point over by 1 spot to get rid of the floating point representation, -1, 1. This is going to be -3 in base 10. And that's the number we were trying to store in that system. I encourage you to rewind back to other parts if they confused you. Check out my other videos that I have in the description if you haven't seen the introductory context of things. And let me know if you have any questions. Okay, I really hope this helped. Thanks, guys. Bye.